Good evening, everyone. I am Bandhuka Kurupu, Technical Events Coordinator for Civil Engineering Section Committee. I think there is some technical issue today. Our host, ISL host CPU is not connected yet. I'm trying to get connected them whether this is recording or not. We need to ensure. So meanwhile,
Excuse
he
me,
was
Bandhuka. Yeah, excuse
yes,
me.
madam.
It's recording thing is going on. Recording is, I can see the recording.
Okay, then we will proceed now, madam. Okay. Okay. Okay, today is the 11th session of this lecture series. So we have completed 10 successful sessions. So our sincere gratitude for Professor Tisanjay Singh for conducting these sessions. And we have received many positive feedbacks from participants about the importance of this lecture series. So thank you very much. And over to you, sir.
Thank you, Bandhuka. Right. Good evening, everybody. Is recording is all okay, Bandhuka?
It's blinking, Professor. I think.
Maybe okay, maybe okay. I was
yeah.
Right. So we'll start from where we stopped last time, and I'll briefly, talk about what we did last time. Last time we said we'll have a continuous beam and we'll work. Do not worry how it was constructed. So if you have a beam like this, you'll get a dead load moment diagram, and then onto this we might have to superimpose an additional diagram that is, that will give the superimposed operator. But we'll again not worry about that. But we'll also now think about the live load moment diagram. Right. Because superimposed dead load is not a major load, so we'll not worry about it. And I told you that we might get a diagram like this for live loads. And I actually explained with the number of diagrams how this could happen. So, right. So now if you look at the bending moment diagram, then it will look like the dead load moment diagram going like this. And a minimum moment, this is negative, so this will go above. That. And this will go below. The maximum will go below. Like that. And if the range here is MRA range, the same location here is this also MRA. So basically we can define a maximum moment MB, a minimum moment MA, and the range M range is equal to MD minus MA. And then we also looked at the manual diagram like that. And this is minus Z2 over A. This minus Z1 over A. And we had two conditions going like that. And we had two more conditions going like that. And we might also have a maximum eccentricity due to the fact that we are having a section like this, where the centroid will be here, and there's a maximum eccentricity Emax that we can place the tendons, the ducts. We cannot place it outside. So because of all this, we'll get a feasible region which looks like this. We get a feasible region that looks like. And then we said there are some special conditions to be met. This gradient of this line should be greater than the gradient of this line. And from that, we said Z2 should be, Z2 is a positive quantity, should be greater than MB minus MA. Compressive stress under working minus tensile stress under working. So we derived an equation like that for a continuous. So that's a summary of what we did last time. And then I also said that when you are selecting the pre-stress, select it in this way as low as possible, as low as possible. Don't select in this region because the pre-stress will be higher. And when you have higher pre-stress, it's going to be costlier. The cost is going to go up. So because of that reason, do not select a high load, a high pre-stress. Always select a pre-stress as low as possible. So that is a summary of what we did last time. This is engineering sectional committee. And today is 16. 5, 2023. It's number 1. So that's a summary of what we learned this last time. And we went up to the manual diagram, we derived the equations, and then we derived these conditions. And I also said these 2 points will be unique. We call it A, B, C, D. These points will be unique, B and D. And so if you select a particular section, the pre-stressing corresponding to this PB and PD will be unique values because they are not going to depend on the cross section. They are not going to depend on the moment. They are going to depend only on the cross section and the allowable stresses. For that also I derived an equation and showed they are not dependent on the moments. So that's also a special situation. That is also a special situation. So with all this knowledge, armed with all this knowledge, now we'll see whether we can design a cable profile for a continuous beam by using manual diagrams. And when we do that, what is going to happen? So basically, for simply supported case, what we do is we have a beam subjected to pre-stressing. Then it will move up like this. We call it moment at transfer. Then it will bend like this when it is subjected to the maximum loads. And we say it is the service conditions where M, D, and ML will act. And then we said draw a manual diagram, select a force, and then you have the bending moment diagram. For each section, draw a separate manual diagram and decide how we are going to arrange the cable. So here we draw the manual diagram at the center, because that is the most, that's the point with highest moment. We select a P, and for that P, so then draw manual diagrams at every other section, and for that particular P, find the corresponding axis. So then after that we say, okay, we are going to get a region like this. So we have two options. One is fit a cable, and generally when we are fitting the cable, we'll make sure it ends at the center. So we fit a cable and the design is over, provided that you have you can do some loss calculations and show the loss that you assumed as 30% is a reasonable value, because generally in pre-stress concrete we assume a loss of 30% from the initial stages, and if you can show that this assumption is reasonable, then the design is over. Then you have to check for shear, provide some reinforcement for construction stages like early thermal cracking, like minimum reinforcement. Then the design is over. But then we also can have another option, and that is what we call, we do this, and we say we are not going to go for post tensioning, we are going to go for pre-tensioning, and we might have another, and we say we are going to have a cable like this, straight cable, and another cable like that, and here we shift the centroid by debonding. By using debonding, we change the location of the cable. So this is what we use in Y beams, M beams, inverted T beams. So this is the method. So pre-stress concrete, if you use this way, is not a very difficult subject. Only thing is you have a lot of calculations to be performed, but they are standard calculations. And so if you are going to get some guideline like this Y-beam charts for Y-beams or M-beams, there are charts for Y-beams, charts for M-beams, charts for T-beams. Then even a person who is not a bridge engineer, but who is familiar with pre-stress concrete design, can very easily complete a bridge design. So it's not a difficult task. Only thing is, once we do come up to this level, either pre-tension or post-tension, then we have to do many other calculations, like we have to calculate the losses as shown. The R value of 70% is a valid assumption. Then you also have to check it for shear, and you can check it for deflections. So those are standard checks that you have to do. And you can easily find the information with examples on how to do things using a book by First. So there's a book, very good book by an engineer published in Singapore. The book by First. Okay, I'll find it and I'll show the book. If you just say type on web the book by Hearst, you will get the information. And that's a very good book. And that the latest edition is written for Europe, so you can easily find how to do the fine calculations. But now today we are going to do the same thing for continuous beams, and we are going to see whether it will work. And I'm actually going to show that it's not going to work. Right? So let's see what's going to happen. So we have a bending moment diagram. So you can see we have a bending moment diagram, and if you have bending moment, maximum moment, minimum moment, you can draw a bending moment diagram, and then you can select a pre-stress, and if you select a sufficiently large pre-stress, what will happen is these are your maximum and minimum boundaries. You can't place any tendon beyond that point. And this is the level where you get centroid. This is the level that you are going to get the centroid. Because the top flange is wider, so this is Y1, this is Y2. And so Y2 will be greater than Y1 because the top flange is thick. So when you do all this, you will find that you select a pre-stress force which is large enough so that you will get a region like this. If you select a too small force, you will not get this type of diagram. But if the force is large enough, you might get a zone like that. Then what are we going to do? If you have a zone like this, now we can fit a profile. So the feasible region will be only this. That will be the feasible region. Is that clear? Because we cannot go beyond the physical boundaries. We can't place the cable outside the section. Now what are we going to do? No problem. Fix a cable. And we'll assume that we are keen that we place it like sections of parabolic sections, and we have these are all parabolic, right? We'll assume that. Then if you have a parabolic profile, if you have a parabolic profile like that, and if this eccentricity is E, the force is P, and then we can say this will exert a load, a UDL upwards. Exert a UDL upwards, and if that UDL has a magnitude W, then we can say W L squared over 8 is the maximum moment that you get at the center, and it is equal to P times E. And because of that reason, we can say W is equal to 8PE over 8PE over S. And we say this is an equivalent load. So what we say is, a pre-stress can be represented like this. So this is the actual pre-stress that we have applied with a parabolic profile, and it is equivalent to this situation. A pre-stress force P at the center plus a UDL acting upwards equal to W, where the W is given by 8 PE over S. And this is called load balancing method. It's called load balancing. So what we are saying is, if you have a pre-stress like this pre-stress is equivalent to an upward force equal to so what we are saying is, we have a pre-stress force like this, and it is equivalent to a system like this, where pre-stress becomes axial and the flexural component of pre-stress is represented as an upward load. And this is a very popular method in USA. They always look at pre-stress concrete as, when you have a parabolic cable, it is like applying a force upwards. The effect of this is applying a force upwards. So this is the method that they use in United States. And if you actually look at it, it's a subtle way of representing our basic equation P over A plus PE over Z minus M over Z. So what we do is, we keep this component like that, and so we have the loads acting due to dead and live loads. So W live. Then we say the flexural component is equal to WP, and then what is remaining? Only the axial component. Only the axial component is. So this is actually this load balancing method is nothing special. It is basically breaking up this equation, into two parts. But this actually becomes extremely useful. This becomes extremely useful when we actually look at continuous this theory of equivalent loads. This is extremely useful to actually explain what's going on in this type of situation. So now you can see a pre-stress force in a parabolic format is equivalent to an upward load W, where W is given by 8 PE over S square. Now let's see what's going to happen. So let's assume that we have fixed this profile. This is the centroid line. And these are the supports. These are supports. And we have fixed a profile like this. It reverses, goes down, reverses, goes down. So that means if you look at this portion, here we are applying an eccentricity, a parabolic profile, length is L1. And here over length L2, we have another profile, here length L3 and so on. So that means if you take this beam now and remove these two supports. In this portion, it's loaded upwards. This portion is loaded upwards. This portion is loaded upwards. And mostly it is loaded upwards. But only at few places it's loaded. Now, if you apply so many upward loads and only few downward loads, what is the most likely scenario? The most likely scenario is this beam is going to move to stop. And to, but can it actually happen in practice? No, because there's dead weight and there are supports. Because of all these supports, what will happen? When the beam tries to lift upwards like this, what will happen? What will happen? The supports will say, no, you can't move on. Right? Now we are going to bring you back. Bring you back. Because beam is not allowed to lift at the supports like this. They are supported and they are not supposed to lift upwards. So what will happen? Now, then we have a situation where we have a beam, long beam, subjected to downward loads. And that will give a bending moment like that. The beam is subjected to two point loads. It will give a bending moment diagram like that. And we call these moments M2. And these at the second support, M2 at the third support. And these moments are, some people call it parasitic moments. Some people call it secondary moments. Some people call it reactant moments. Why reactant moments? Because the reaction is causing the moment, so it's called reactant moment. Some people call it secondary moment because it was not there initially, now it is happening. And some people call it parasitic moment because it's a real pain. Used to be a real pain, because what happens is, now you do your load analysis, right? And we have already got a bending moment in top. And we have MB, we have MA, we have fitted a cable, it's fitted. Now what happens? Now we are getting an additional moment M2 as well. And it's a second moment. which means now we have drawn a McDonald diagram using this moment diagram. And then after doing everything, you fit in the cable, everything. Now you are getting an additional moment. Then what is the total moment? Total moment is MB plus M2. MA plus M2. So basically it's like, you start designing, saying that the bending moment MA, MB is 150, MA is 110. And you do all your calculations, draw McDonald diagrams, with very carefully find the force that works throughout the length of the beam. And then you fit the cable and suddenly you find this MB is not 150, it is 180. And MA is not 110, it is 140. Now what will happen to your calculations? All will go wrong. So this was the problem faced by engineers who tried to design pre-stressed concrete continuous. So because of all these difficulties, many engineers thought, okay, why do we want to make it continuous? Can't we make wood bridges by using simply supported bridges? And this, this pre-stressed concrete continuous bridges is the real pain. Because, you can't do the calculation. So every time you do the calculation, you find after doing the calculation, now the calculations are not valid because the bending moment has changed. So what did they do? They thought, this is a real pain. We cannot bother with all these things. So let's do this. What did they? What they thought was, okay, let's cast the beam separately and then put some reinforcement. And anyway, you will have a continuous stopping. And make this area solid. Put some reinforcement. And make it continuous. Only for nylons. Continuous only for nylons. Because we are going to do it this way. Because, designing a continuous pre-stressed concrete beam is nearly impossible because you do a set of calculations, spend a lot of time, find a cable profile, find a pre-stressed force that is going to work throughout the length of the beam, and then you find the fitter cable within the cable profile zone, and basically these are zone. You can see these are zone. Here what you get is a zone. And so what you get is a zone. So we say we are going to fit a cable within the zone. Right? So this is a cable profile zone. Cable profile zone. Not a line, it's a zone. And within that you can fit a line. Right? It's perfect, but after doing all these things, suddenly you find some strange moment is coming, and that is going to derail all your calculations. So people thought, okay, why we worry about it? Let's do simply support. So in Sri Lanka also, we have few box girder bridges that we design, and knowing the construction limitations of the contractors, we also adopted the same. For example, Orugodawatta flyover we used for box girders. Like that, giving a total width of 17.6 meters. And then there are many bridges, again eye girders. like the bridges on A15 highway on the eastern province, or also two bridges on A4 highway on eastern province, because you know A4 is the longest highway in Sri Lanka. Starting from Colombo, it goes all the way up to the eastern coast, and then it goes along the eastern coast up to Batik. So it goes close to Panam and then it goes up. So in that area, we have two bridges, and A15 has 5 bridges. And then this is one of the longest and widest flyovers in Sri Lanka. And that is Orogodotha flyover. It also has box girders. And there are many others besides that were done by Japanese bridges, you know, bridges constructed using Japanese laws, then and rams. Some of them they have actually gone with this with continuity, but most of the things we have done, we have actually limited us to this, because this is the kind of joint that we used. We have the beam, and we have another beam, and we cast the top slab continuous. After casting, actually we cast it in 2 stages. So here we actually had a double bump, and we cut a groove and fill it with polysulfide. And this double bar also, one side embedded in concrete, on concrete, other side wrapped with polythene. This side is wrapped with polythene, and both are embedded in concrete. So any movement can be easily accommodated. So we use this particular joint, and then what we did was we actually laid concrete. And if you want, you can layer geotextile. So this was done, and it was very successful. No problem whatsoever. You can't see the expansion joint, because there's no expansion joint as such. It's only a kind of a continuous joint. Actually, if you do the calculations for Sri Lanka, you will find expansion joints are anyway not necessary, because our thermal movements, the diurnal change in temperature, that is the daily temperature change, is very small. So because of that reason, even if you don't provide any expansion joint, in Sri Lanka, bridges cannot have any problem, especially the concrete. It's not the steel. The steel bridges can have problems, but concrete bridges will not have any problem. So that is the normal situation. So anyway, these have worked well. But now we have to see how we can design a continuous beam with avoiding all this trouble. So that's what I'm going to explain now onwards. So we have to first understand why we cannot design a continuous bridge as we do with simply supported, because of this situation where you do all your calculations, get a zone. Because before getting that, you have to draw the manual diagrams at each critical section, that is here, and then see which pre-stress will work. And sometimes here you will find the pre-stress has to be 18,000. Here you might say 20,000. Here 22,000, and then here again 18,000. This 17,000. Then you will say, okay, I'm going to select 22,000, because we always know the minimum will not work, but a higher value can always. So out of all these, the highest is given here as 22,000. Then we might select 22,000. So once you select 22,000, we can draw manual diagrams at every section, and from the manual diagram we can find what is the upper limit, what is the lower limit. Whenever you have two limits, we can't get a line, we have to get a zone. And this zone is for cable profile. So we call it cable profile zone. Right? We call it cable profile zone. Then you have to see, right? Then you have to see, right? Okay, now we have figured it. Then I said, this American method of this test, again, it's not anything special. We are just breaking up our normal equation into two pieces and presenting. And I said, if you fit a cable like this, we are going to get some loads acting upwards, some loads acting downwards. So what we do is, once we allow it to deform freely, you will find generally these upward forces will be far more than the downward forces. And because of that reason, the beam will be lifted up. But in practice, beams cannot lift up like that. So because we are not allowing the beam to lift up, there will be forces acting downwards. And these forces will give rise to a sagging moment diagram, right? And so you get a bending moment diagram like this. And I said, because of this sagging moment diagram, these moments are going to increase. These moments are going to increase. So what is the reason for increasing the moment? So what actually happens is, you have to add these two diagrams. And this is a sagging moment. So you can see, if you are adding a sagging moment, this will increase. So what we do is, when you want to add two bending moment diagrams with principle of superposition, and if this is sagging and this is the normal envelope, this is sagging, what we do is, we actually mark M2 here, mark M23 here, and then we'll draw a line like this, and we consider that as the new origin of the bending moment diagram. New origin. So what happens? Now you can see, now we measure the bending moment from the new origin. So if it is earlier 150 and 110, now it's going to be 180 and 100. So that's how the bending moments increase. So basically, whenever we have two bending moment diagrams that we want to add, we can use principle of superposition. And in principle of superposition, if this is a sagging moment diagram, this hogging, this sagging and hogging both, this sagging only. So what we do is, and it's because it's varying linearly, we can mark M2 to as a hogging moment, because we know when you add this to this, the moment should increase. So the only way you can get a moment increase is by representing the secondary moment diagram on the hogging side. And then we assume that that is the new origin of the bending moment diagram. And automatically you can get these numbers from the bending moment diagram. You don't have to do it mathematically. So that's a graphical representation of principle of superposition that you all have learned in the maybe the second year or the second semester. So by using principle of superposition, you can easily work out that the bending moments are going to be like this, where the bending moments in a span section will increase. Bending moments over the support section will decrease. Now let's see. Now we call this moment parasitic moment, secondary moment, reactant moment, and most people use this term because parasitic means bad. But I'm going to show you it's not bad, it's good. Second means small, right? But I'm going to show you it's not small either. And reactant is okay, it's due to the change in the reaction, so we can call it reactant moment. So I will be using this term secondary or reactant moments interchangeably, but you have to keep in mind secondary means generally small, but these moments need not be small, they can be large. And reactant means due to the change in reaction. That's a good term. And parasitic means bad. But I'm going to show you they are actually good. Now let's see why they are good. Then we can see how to make use of it. So why are they good? Now let's see. Now what will happen due to secondary moments? We have a bending moment diagram. So it's 3 square, right? And it's a section like this. Our section is like this for highways. Why? Because we are going to have the vehicles. So, because we are going to have the vehicles here, we need a wide flange. So, anything having a wide flange is a flanged beam. Which one is better? Rectangular beam. We all know flange beam is better. Why? Because concrete is a material that can carry compression in it. And if you have a flange, it is more efficient than a rectangle. Why? Because the concrete is there to carry compression. And when it is subject to sagging moments, what do you get? Get compression here. Compression. And the same section subject to sagging, here you get compression. But because flange is in tension, we can't make use of the concrete in the flange. So what is good there? If we can reduce the bending moment at the support, and within brackets I'll say with the corresponding increase in span. Is it good or bad? Yes, good. It is good. Why? Because this is very good in carrying sagging moments, not very good in carrying hogging moments. Now what are we doing? We are reducing the moment of the support and increasing it in the span, and that is exactly what we would like to have. So you can see, okay, these moments are not bad. They are okay, they are okay. And they are going to do this kind of change to the bending moment diagram. So we're going to have large hogging moments, right? But again, we have to be practical. Why? We know that when we fix the cable, what is the moment we have? Now, we don't have the vehicles on the beach. What do we have? We have only the dead road or the self-weight. So we say secondary moments, when you have secondary moments, they should not be too large and can be a percentage of self-weight. If they are too large, what will happen? The beam will lift up and there will be big trouble for you because it has no stability. The beam lifts up. So we like it to be hot. So we say, so what we do is we'll consider the beam and consider its self weight MD, and so we draw MD diagram. And let's say these 12,000, these 14,000. We say we might go for 0%, 30%, 50%, 70%. Maximum might be about 80%. Why? Anything more? Too much. We will not have stability during construction. If you talk about more than 80%, then they will not have stability. So we can say, then we can have a rule. What is the rule? You can even have say 0%. Because then there is no advantage. And if you say 30%, you are taking only part of that. If you go for something like 50 to 70% or up to 80%, then you are making a substantial portion of that. So generally, I would like to stay somewhere 7 to 8% of the dead load moment. So if you are going to have 7 to 80% of the dead load moment, now I'm going to mark those values and then draw a new origin for the bending moment diagram. Draw a new origin for the bending moment diagram. And then all the moments are measured from the new origin. So MA will increase, MB will increase. Here also MA increase means this MB increase means actually its magnitude becomes more. Right? Because it's negative, when you are reducing a negative value, it's increasing. But if you look at the magnitude only, what has happened to the magnitude? Reduced. Earlier, the magnitude used to be this. Now the magnitude has been. So if the magnitude has reduced, what is the advantage? It's going to behave like a rectangular here, flange here. So flange, high moment. Rectangular, low moment. Good. So these moments are not bad, they are good. The problem is how to make use of them. How to make use of them. So for that, actually we developed a design method. What we said was, okay, we have a beam. We have already selected the cross section. How did we select the cross section? Because we know we need 10 meters out of flange. Why? Because I am going to have 3.2 lanes of 3.5 meter each and 1.5 meters for workpiece. So I need 10 meters. So that means we need 10 meters. Then we can have overheads. Then we need a web. Why? Because this is long. So this is we'll have to carry shear. So we need a web. Okay, let's have a web. The webs. We need a bottom flange. Why? Because this is going to bend in the wrong direction over the support. So we need a bottom flange. We need a top flange. We have to make it hollow. Why? To reduce the weight. So we need a top flange, we need webs, we need a bottom flange, we need chamfers. Why? Otherwise, there will be stress concentrations. So we have a section. And in this section also, we say is very good with sagging. You have a small bottom flange, so it's not good with sagging. So we have very good reason to reduce the moment by using secondary moments. And we can go up to about 70 to 80% of dead load moments. As in, so the design method what we thought was, okay, let's see. One, select a section. Select a section. Now, when you are selecting a section, do you have to worry about the secondary moments? No, we select the section. And we have to control the reflection. So, span now over depth has to be something like 80 into 25. You can't have 50. So when you look at the some of the bridges that have already been completed, then you can easily see they have maintained values like 80 to 25. Will also be in that range. Then perform dead load, live load, and get bending moment and any loads. Get a bending moment in that will have MA and MB. MB is the bigger moment, MA is the small. Third one, assume second reactant moments to be part of self weight moment. So we can say 60 to 80%. Then obtain a so then use Magnum diagrams and find a suitable P. There is a P valid at all sections. Select a suitable P. Use Magnum diagrams and find a suitable P. So what we do is, when you look at these, once you select the section, you know the dead weight of the section, and you can analyze it as a beam because the is torsionally very stiff, and so you can apply all the loads, ignoring torsion, and get the total bending moment just by analyzing the beam. Then later we can refine it with wedge analysis and all that. But initially, because we have no information, we can analyze it as a beam. Assume reactant moments to be part of the self-weight moment, because we know the friction, we can find the bending moment value. And then use Magnum diagram and find suitable P. So we have this and this, and at the end of all this, and then the modified MA and MB values, and this is the final bending moment. Because now we have already got the second moment in, that's the final bending moment diagram. For the final bending moment diagram, we draw Magnum diagrams and find P. So P might be 18,000 here, and it may be 20,000 here, and 70,000 here, 22,000 here, 15,000 here. So P 22,000. So we select a P. the maximum at critical section. So this one critical section, this is another 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 critical section. So you select the critical sections. The critical sections are the ones having the maximum sagging moment or maximum movement. From that information, you can see that we can select a value, and let's say that we select as the highest of all the critical sections. And from all the critical sections, we select what are the values needed, and out of the highest, out of those, we select the highest. We select the highest. So now we have selected the pre-stressing force. So once we select a pre-stressing force, as I have shown you, we can draw a profile. We can draw a profile. So what we do is, we will, now we have all the information we need because we have the final bending moment diagram. And what we do is, this is the centroid, and we might get an upper profile. That and a lower profile this. And then upper and lower limits. So we can't have the tendons outside. Tendons must be inside and should have sufficient cover. And then now we have all this. Now we have to select a cable profile. This is a cable profile. So cable profile. So, right. Now we have to select a cable profile. It has to satisfy two conditions. One is it should be within limits. Within limits. It's one. What is the second condition? It must generate the reactant moments that we assumed at each. We have already fixed the reactant moments. Now you can generate something else. Then again the calculations. So we have done calculations in one direction. Now we have a special condition. Fitting something within this is not a major problem. But the problem is you have fit something within these set limits, which at the same time ensure that it will generate the assumed secondary moments. This is the trick. This is the tricky part. And how are we going to handle that? And for that, we are going to learn a new term. Last time, one person asked this question. Are we going to use concordant profiles? Are we going to use concordant profiles? The answer is yes. So what is a concordant profile? Concordant profile is one that generate 0 secondary moments. 0 secondary that generate 0 secondary. Now, how are we going to have a profile that generates 0 secondary? And again, some theory comes to our rescue. And the theory is simple. Any a bending moment diagram due to any set of modes on the given beam is a concordant. So something has come to our rescue. A bending moment diagram do any set of it can be a point load, it can be distributed load, it can be a load acting upward, it can be a load acting downwards. You do anything you like, any type of loading. Get a program like SAP 2000, model the beam, and then apply any type of loading, whatever type of loading you apply, point loads, UDL, SAP will analyze it for you and will give you a bend. And if you can fit that type of bending moment into a zone, then it will generate 0 secondary moments. It will generate 0. So what you have to understand is, if you fit a profile which actually represent a bending moment diagram due to a set of forces, it will generate 0 secondary moments. Why? Because when we are applying loads, what is the deformation at the supports? We assume that the supports are not set free. If supports are not set free, supports are there, then you will find the curvatures induced are compatible with 0 secondary moments. So if the secondary moments are 0, can the beam lift up at the supports? No. That means the curvatures that you get due to a concordant profile will be compatible with the curvatures that you get due to any set of loading. So if you fit a profile along a bending moment diagram, then the curvatures will be compatible, 0 settlement or 0 uplifting at the internal supports. And that is exactly what will happen in the case of M2 equals 0. So any bending moment diagram, a real bending moment diagram due to any set of loads will be a concordant. So now we have to see, where are we going to fit it? We can't fit it here. Why? Because this has M2 values we have already used. So we now use something called linear transformation. Linear transformation. And linear transformation, you see, P times ES is equal to P times EP plus M2. So then it says EP is equal to ES minus M2 over P. So in linear transformation, what we do is, now we have a zone inside the beam, and it will go like this, to go like this. And you can see this is very similar to what I have drawn, is very similar to this one. So if you look like this, so what I do is I will use this equation and then find something called it can be even outside. So what have I done? Now this has M2, this has M2, but for this I have removed M2, so for this M2 is equal. Because I have used something called linear transformation and transferred the cable profile to a line of thrust zone. So this is a cable profile. So that means the cable must come inside that. So what is this one? This is the corresponding line of thrust. This is the corresponding line of thrust. So what I have done is, now if it is a line of thrust, that means M2 is 0, then what I can do is I can actually fit a bending moment diagram into this. But it's a trial and error process. So for the selected pre-stressing force, I will apply a set of loads and get a bending moment diagram that will fit inside that. For that, what I do is I will model this beam on SAP 2000, and I will so I need something sagging, so I need to have to apply these loads. Then from that I will get a reaction, and I need a smooth curve here. How to get a smooth curve? So what I do is I will get this support reaction and then apply it as a distributor. So when I do this, what will be the shape of the bending moment now? And if I can find a set of loads, that will give a bending moment diagram that fits inside the line of thrust zone, then the job is done. Job is done. Why? M2 is 0. M2 is 0. Then what I will do? Then transfer EP selected back to ES using ES is equal to EP plus M2O. You bring it back. The moment you bring it back, you will get a new diagram like this. There's a new diagram like this. And what is the specialty? This now diagram will generate M2 that you have assumed. So we can numerically show on our spreadsheet if we do this calculation. Using this method, we can prove that what is assumed is obtained. What is assumed is obtained. So this is a design method that we developed at Cambridge University somewhere around 1989-90. So that is some 30 years ago we developed this method, and using this method you can very easily design a continuous beam, and because there are so many sections involved, now we have put it onto a spreadsheet, And by using a spreadsheet, we can show how this can be done numerically. But the important thing is to understand the theory. Theory is, right, there's something called linear transformation, that is that you can find on any textbook. And then there's something called concordant profile that you can find on any textbook. The concordant profile is a profile that does not generate second limit. Linear transformation is finding a line of thrust from a cable profile. Right? So those are standard methods that are there. And using all these standard methods, we have developed a method where earlier problem was you did not consider M2 and suddenly it appears at the end of the list. So what we did was we brought it to the front. We said, okay, we are not going to be bothered with M2. We are going to assume M2 and then ensure whatever assumed is generated. Then we don't have to go in a number of cycles trying to figure it out, because it's one-way operation, not a trial and error operation. Because we assume a value and we generate whatever we use. But we assume something reasonable so that during the construction, the beam will not become unstable. So before that, we have to make sure we assume something between 0 and 80% of the dead load. So that is the method. And so I can show how this method can be used for designing a pre-stressed concrete beam next time by using a spreadsheet. And you know, spreadsheet based calculation is the best for pre-stressed concrete design, because at every section we have to draw a magnet diagram. To draw the magnet diagram, we need data. So we have to ideally just do it with a spreadsheet, so that you know even the drawing of the magnet diagram can be automated, because there are only 4 equations. So we can even draw the magnet diagram using some of the graphical facilities available on spreadsheet, but I don't go to that level. I will simply find the limits for a given pre-stress force, and then I can numerically show that this method works. So any questions? Any questions, please? So next time I'll show you how this works using a spreadsheet.
Yeah, Professor, I'm here.
Yeah.
There are no questions in this chat box.
Maybe?
There are no questions in the chat box.
No questions in the chat box. That's right.
Chat box. So yeah, you can decide what.
Yeah. So basically, now it's time is also almost up. So I can actually scan this and send it to you, share it with you. So just have a look. I have explained it in great detail, and I have showed that, you know, with all these diagrams, that what we are doing is a method, right? So it's based on theory, but to show it that it actually works, I have to get a real example and then perform the calculations, right? To perform these calculations, like, you know, something like finding the bending moment diagram due to a cable profile, those things will need a little bit of special details, some special techniques. I can show those techniques as well, because when you are preparing a computer program, you have to make sure everything is based on equations. Otherwise, you can't put it to a computer program. Even in a spreadsheet, it's the same thing. So I will show you there are a few special things. Without proof, I'll show you initially, and then later I'll show the proof as well. So next time I can actually show you how this method can be used to design a continuous pre-stressed concrete beam using a spreadsheet. And basically, within 2-3 hours, you can design a beam. continuous bridge using this method, because we are doing all the calculations only in one direction. We are not doing any trial and error calculations, because everything is well set, because we are going to assume the values initially and ensure those are generated. So that is the method. So shall we end the lecture, and next time I'll show you how it can be done numerically.
Okay, Professor?
Yeah. So next time I can show how it can be done numerically. But today I explained the method, and next time I'll show you how it can be done numerically. Right? So that you will gain the confidence that it's a method, and I can share the spreadsheet with you as well. So you can actually use this method for designing spans 80-100 meter long bridges. This method works because this allows you to optimize the design while taking into account the construction situations, the situation that arise during the construction. And the examples, currently we are having port access road elevated, that is continuous pre-stressed concrete box girders, and that is being completed, and civil engineer sectional committee had a visit to this particular project as well. So once you understand this theory and once you have the spreadsheet, you can even design that type of large bridges. Okay.
Yeah, Professor, then I think one is having some connectivity problems. So
okay.
Shall I do the winding?
Yeah, please.
Yeah, okay. Yeah, actually, I think I am Kamala Gunawardana. Maybe you all know me. I'm chairing the Civil Engineering Sectional Committee this year. So, Professor, thank you so much for shouldering the responsibility and delivering most fruitful series of lectures, even this year.
Thank you.
My gratitude for your contribution, taking many hours out of your busy schedules. Actually, it's going well ahead because so many comments and appreciations are coming from all over the world. So it's a great thing for us. So thank you once again.
Yeah, thank you.
This is the 11th session of this lecture for this session on this subject. So also I thank Engineer Banduka for his excellent coordination and sharing all these links with the participants and sharing every matter what involved in this. So thank you, Banduka. Also, I especially thank the participants. You all are taking keen interest, and I hope you got the most of the stuff what he delivered, Professor delivered today also. And I thank our technical team and the secretariat of the ISN for helping us to do this event as a very success. So thank you so much. Hope you enjoy the lecture and wish you all the good night.
Yeah, thank you. Thank you very much. Thank you.